log 10, a little bit of math. Okay, log 10 nt is equals log 10 and 0, and then becomes log 10 2 n. This is, you know, is that right? Log n0 multiplied by 2 times n is going to become a plus when you have a log 10 there. And we will measure log 10 in the lab also, because that's a message to calculation the bacterial cell. Because it's too large, we have to change to log 10. Now what we do? Log 10 to n z equals log 10 nt minus log 10 n 0. Okay? And then we can need to test to that n. So what's the n going to look like? N going to put right here. So n becomes log 10 nt minus log 10 n 0 and divided by log 10 2. Okay, now a little bit of math. What is log 10 2 equals? You have to guess. 10x equals 2. What's this one looks like? Somehow 0.3. Okay, you can use calculator. It's easy. I know it's 0.3. So this will be replaced with 0.3. And this is a generation number. And after certain time t, therefore we come out with a kinetics which is k equals growth rate. And that growth rate equals log 10 nt minus log 10 n 0, which is at the beginning, then you divide it by 0.3, that is log 10 2, and you need a time which is t. Okay? That's a growth curve. That's a growth rate. Now what is going to happen? When we talk about the generation time, this nt equals 2n0. 2 multiplied by n0. So we're going to replace this. When you replace this, what's going to happen? This becomes log 10 2 added log 10 and 0 and then minus log 10 and 0, and then go here, it's going to become 0.3. This t, we have a special number called g because it's a generation. So we put a g there, which means generation. Generation time. Now, these two, you go, and the log 10, 2, and the 0.3 are the same. So what it becomes? That k equals 1 divided by g. And we usually don't know g, we know the k first. Because the k, we could do a set of experiments to find it. So at the end of the day, the generation time, which means the doubling time, this equals 1 divided by k, which is a growth rate. We also call it a reciprocal number of a growth rate. Okay? Reciprocal number of growth rate. That's the whole formula there. And you can look at the slides, which is tells you. This is gives you some idea. You only need to know is the conclusion. The generation time and the growth rate, they multiply them together equals 1. And that is what the mass behind it. Okay? Now, we want to measure why the bacterial cell we have to use log 10. There are a lot. For example, I have 2 times 10 to the 8. Some 2 times 10 to the 7, 2 times 10 to the 9. This huge number, we cannot do statistics analysis because it's too large. They will generate lots of errors. So I have to make sure this error is under control. Therefore, in the microbiology area, we do a log 10. Then these numbers will become very small. For example, this is approximately 8.3 log 10. This is approximately 9.3 log 10. And this is approximately, let's say, 5, that will be 5.3 log 10. And at the end of the day, we are comparing these 3 numbers. Instead, we're comparing that giant number, which makes you math a little bit easier. That's why we change them to log, because it's too much. Okay? These type of things, we have another discipline to talk about. It's called predictive microbiology. But I give you some of the introduction. You need to know there's a math behind it. Most of them right now, they have a software. So not really do the manual. You have the software, you put the number, will be automatically generated. Okay, so that's for the generation time and the growth rate. Now the key point here we really want to talk is not these giant mass, but it's not a mass class. We want to talk about something very special for bacteria, is the bacterial growth curve. When you look at the slides, you will find it's very special. So if you never take a microbiology class, you will simply thinking a bacterial growth. Let's say you have a time, x-axis, okay? This is the population for y-axis, number. You will think the bacteria grow just like this. It is not. If it is like this, then your agar plates will look so horrible in the lab. Remember, we grew them last week, is that right? Today you see it is still fine. It didn't mess it up and become the whole agar covered with everything. That means bacterial growth is not linear. You have to know, this is the first thing. Okay, not linear. So what it looks like? This is something you definitely need to know from this class. Y-axis represented by time. Lots of the time they use hour to express it. Y-axis is population. That's a cell population. Most of the time we actually using CFU, colony forming units per ml. So CFU equals colony forming unit, which means those single colony on the plates, that's a colony forming units. Now what's a curve looks like? A very special. At the beginning it is very flat. Then becomes very sharp slope. Then becomes flat again, and they started to drop. This is a bacterial growth curve. Because the bacterial growth curve have 4 stages. At the beginning we call it a lag phase. What's the function for lag phase? Bacteria transfer to a new environment, they need to do some of the adjustment. So basically DNA, RNA, protein, okay, cell, they'll do the preparation. They need a time to accustom to the new environments. So at that moment, the bacterial growth is very, very limited. Once they adjust to the environment, they're going to grow dramatically. Therefore, the second stage, we call it a log phase. Same thing like we did with log. This slope is going to grow dramatically. Really fast. But they're not going to grow all the way. Okay? Because bacteria grows, they're going to generate the metabolic waste, which is a toxication. The toxication material will be accumulated in the cell medium. It's a toxication for the bacteria. So they have to battle those things. Therefore, they reach a stage which is called stationary phase. The stationary phase, which means at the moment is balanced between nutrition, nutrient, and waste. So the bacterial number at that moment is very stable. But after that, they compact with those toxications, they need energy. When the energy depleted, they start to dead. Therefore, the last area is called the death phase. The bacterial number started to die. Generally speaking, you see the broth in the morning. When you grow the bacteria, we incubate it at 35 degrees Celsius, 24 hours. How long it will be there? About 48 hours. After 48 hours, they start to decline. And then you can put it into the refrigerator. You can storage it. How long? About 3 weeks. After 3 weeks, it started to die. So that means later on, somehow like that. But I want to keep it cautious. Lots of the time, although they go to death phase, does not mean this bacteria is zero. They may be still there. Sometimes there's a big chunk of bacteria still right here, and you cannot even test it. But they are still could cause a problem. This comes out with a very tricky concept called a viable but non-culturable. The research area has been doing this for a lot. We talk about the sampling plan. So let's say we have a meat plant. We're going to go ahead and do sample. I have 100 beef patties. I'm using PCR methods to do the rapid testing. And lots of the time I find it's zero. But how come this batch still causes a problem? They cannot go to the market because some of the bacterial paracel is viable but non-culturable, which means they're pathogenic. But you cannot use traditional methods to grow them. The toxication is still there. It's very tricky. Now why? Because bacteria die, same as our human being, we call it a programmed cell death. It's the programming after it to guide it to death. And in the human being, we talk about the programmed death also. Every cell will become programming death. If there's a problem comes out, what's going to happen? It will become a cancer. Is that right? That's what the side results happen. It's same for the bacteria. Okay? We want to talk about too much about the viable but non-culturable. We just gave you the concept. That could talk a whole class. Lots of the research talk about that. Very tricky and a big risk for the food industry. Okay? Now we're going to move on to something relatively easy, but not that easy. What are the factors going to impact the bacterial growth? The very simple. Number one, pH. How acid it is. Number two, temperature. So what's the temperature it is? It is a refrigerator temperature better, or the room temperature better, or maybe 35, or maybe hot temperature is better. Then we want to talk about is water activity. this is a very tricky concept. Lots of people don't understand this very well. So we're going to explain to you. The last one, oxygen requirements. Remember we mentioned about aerobic respiration, anaerobic respiration, facultative bacteria. This is related to oxygen. Okay? So we want to talk about these one by one. Number one, pH. Very simple question. Review your high school chemistry. What is pH? You should all know. Minus log 10 H plus concentration, hydrogen ions. Because we add a minus there, therefore it becomes a positive number, otherwise it's a negative number. Which means how acid it is, how much hydrogen ions from a log base to express it. What's the range? 0 to 14. Okay, right in the middle is 7. Do you know which one is indicator pH 0? And I tell you something you know, you never noticed. When you do recycle, did you do recycle? Or you just put everything in the bag and throw them away? Some people just throw them away, everything. Is that correct? If you really do recycle, the dead old battery, you should never put in a trash can. Because the battery acid is pH 0. So pH 0, battery acid. That's why people say they're the battery, definitely recycle. Even you have to package it. That's a reason, pH 0. Okay, what is the pH like 2? Like 1? Stomach acid, very acid. Stomach acid. How about the lemon juice? Maybe 3 to 4. Is that right? Lemon juice. Okay, what is a pH 7? Yes, some people say water, pure water. But I want to tell you one thing. When you really test the pure water, what's the pH level? Around 5.5. Because chlorination there. And some of the other chemicals there. Never 7. Especially in this mining mountain area, the purification to pay much attention to that. So ideally 7, but most of the time you see 5.5. Little acid. What is pH 14? Very alkaline. What's that? 1 mole sodium hydroxide. Okay. That's no example. It's very alkaline stuff. So based on the pH requirements for bacteria to grow, we have acidified. Or we say acidified. Acidophile. Okay? That means the bacteria can survive, microorganisms can survive 0 to 5.5 pH. Lots of the fungi can survive that. Not many bacteria can go that low. Most of the bacteria we call it a neutrophile. Neutrophile, their pH 5.5 to 8.0. This is most bacteria. Now, there is a certain bacteria, which is Bacillus, Micrococcus pseudomonas, could grow in the alkaline environments. We call it alkaline file. This is usually 8.0 to 11.5. No more than that. Most of the bacteria will be dying. Okay, Micrococcus. Pseudomonas. That's why Pseudomonas is a sporage bacteria and a bacillus. Some example. Okay, that's for the pH. But pH, we have something else going to talk. It is very interesting because we talk about the acid. The acid really going to damage the bacterial cell. If it's too much acid, it could be destruct the cell membrane system, the integrity of the cell wall system. So what happens? If lots of the acid there, when they come out, the bacteria are going to repel it. And how they repel? Exchange with potassium lots of the time. This is number one. Normally it happens. However, there is a big risk. When we talk about E. coli O157H7, and we say that it is a zero tolerance in the beef products. You're not allowed to use one cell. So what do people do? Let's say this is a beef chunk. Here beef. People spray lactic acids. It's antimicrobials. People spray acetic acids. These acids will kill bacteria. However, some bacteria will survive, become acid resistant. And these acid resistant bacteria is a big risk for the food industry because later on when the beef go into thermal inactivation process, it will be resistant to the certain temperature. That is called cross protection. So, in order to prevent the acid resistance, number one, the concentration, you have to follow the regulation. Number two, you need to prepare at least 2 different sanitizers to do the rotation. Sometimes you use acidic-based antimicrobials, sometimes you're using chlorine-based antimicrobials, sometimes you're using others. So do the alternative to prevent that acid resistance. Okay? Because acid resistance, when it happens, they're going to start to activate a heat-stable protein or heat HPR or like other different stress-adapted proteins. So makes it cross-protected in the further antimicrobial treatments. So that's something I want to mention briefly in this class, and we talk about pH. Temperature. That's the second topic. We want to talk about temperature. It sounds very simple, but lots of the things we want to mention. Second one, temperature. First of all, bacteria's temperature. This is temperature, okay? This is growth rate. It always like this. There is somewhere here is a minimal temperature. A little bit higher temperature will reach maximum and always have something is optimal for bacterial growth. We call this optimal temperature. Now why? Because the temperature related to the enzyme activity. It's a very simple concept, enzyme activity. At the beginning, when the temperature increased, the enzyme activity will be increased. Around like 10 degrees Celsius, the reaction will double until they reach the optimal temperature. But after that, it's not going to grow that dramatically. The growth is inhibited because some of the bacteria at high temperature, they will break down cell membrane. Remember Freud mosaic model, double layer integrity. So that's why it starts to drop. Some very high temperature, they're even going to kill bacteria, requires a lesser impact. And you understand it starts to killing it because it's too hot. Okay? So that's something we want to mention. Every bacteria have minimal, maximal, and the optimal temperature. We certainly in the lab grow bacteria, we want them in optimal temperature. Now, based on the temperature requirements, we could be categorized bacteria into basically these 5 groups. Number 1, cyclophile. Okay, we call it a cyclophile. Cyclophile, the bacteria usually grow 0 to 20 degrees Celsius. These bacteria are usually environmental bacteria. Not in the lab, it grows in the deep ocean, in the Antarctic area, in Iceland, also the very cold area. Okay, that's cyclophiles. Second group, cyclotrophs. Okay, cyclotrophs, T-R-O-P-H. This bacteria is tricky. They grow 0 to 35 degrees Celsius. And I tell you one thing, this happens. Most of the bacteria didn't grow in the refrigerated temperature. The other bacteria is cyclotrophs, and we will mention lots of time. Listeria monocytogenes. It's a big risk for ready-to-eat meat, for ham, for turkey breast, for hot dog. Even you do a vacuum package, it's not going to solve the problem because it grows at 4 degrees Celsius very well. And there's tons of research showing that. This gives you trouble. Because at 4 degrees Celsius, we do vacuum package, a couple of days later we find it's growing. And when they reach toxication level, it's going to killing people. That's what outbreaks for Listeria happen. And this guy is tricky because it can grow at refrigerated temperature. It's a cyclotrophs. Some species of Pseudomonas is also cyclotrophs. That's why you cannot put your foods in the refrigerator for extended time. It will start to spoil because spoiled bacteria is also lots of them are cyclotrophs. That's happening in our real life, okay? Most of the bacteria is mesophile. Their growth temperature 20 to 45 degrees Celsius, including E. coli, Salmonella,